Okay, in lecture 10, we are going to discuss about segmentation. So in the very first lecture, we introduced very briefly what is the segmentation task. So we can quickly review that first. So the classification task is given an image. Our task is just figuring out what's the main object or the topic of that. And we just classify them as a cat in this case. And no special extent is inferred in the classification task. And we've done just done the object detection part in lecture 9. So there we detect all the target objects which belong to dog or cat here. And then also we wanted to locate them where they are in terms of the bounding box. That's what we've done in the previous lecture, right? So we covered these two tasks so far. Today, we're going to cover these two other tasks, which is the semantic or instance segmentation. In the semantic segmentation, we would like to classify each pixel, not the entire image, but each pixel-wise classification with, to the set of the classes. So, for example, this some pixels here belonging to the cat, but here they are belonging to the grass, and this part belonging to trees or trees, and these are belonging to sky. So we here also have the set of classes predefined, and among them we would like to classify each pixel which class they belong to. So the output should look like this. So we can see that the cat is here, and the grass is here, and the sky and the trees, something like this. Instance segmentation is similar, but it's a little bit different. Suppose we have more than one dogs here, like this. And if we just do the semantic segmentation, then these two are just the red and green. They are still dogs, and we don't distinguish they are 2 dogs or 3 dogs and which one is which. We don't care in this semantic segmentation. Dog is dog, cat is cat. In instance segmentation, if there are more than one object observed, then we would like to classify them, segment them like the semantic segmentation, but at the same time, similar to the detection, we would like to locate each of those separately. So instance segmentation can be seen as a kind of combination of the object detection and the semantic segmentation. So today, we are going to talk about the semantic segmentation first, and then instance segmentation. So let's start with the semantic segmentation. So here's the definition of the task. So you are given a training image, and each pixel is labeled with a semantic category. So the training data looks like this. You have an image, and you have the pixel-wise annotation, which class each pixel is belonging to. Something like this. And of course, you have to have the set of predefined set of classes here. And at test time, you are given a new image, and your task is classifying each pixel in this new image like this. So you don't have to differentiate the instances. We have 2 calls here, but just call pixels are call pixels, and you don't have to distinguish which pixel is belonging to which call. Only care about the pixels. So that is the definition of this semantic segmentation task. So how can we solve this problem? This should be, it looks much more difficult than the classification or the detection task because this is pixel-wise, so it looks much heavier computationally. So what should we do? What we need is a mapping from an input pixel to the pixel category. Right? Each pixel needs to be mapped to the class scores, and we may take the maximum of that. So from a single pixel to category, it's actually we cannot do anything, right? From the black and what is this? And can you say that? So it's not possible. So we need to take care of the context nearby that pixel or even from the entire image. So for each pixel, you may take a small image patch centered on each target pixel and then classify it. So something like this. Given this image, for example, we would like to classify this particular pixel Then you take the nearby image patch like that, and then you feed it to some convolutional neural networks to classify what is this. Then you can actually train this model based on the label from the center pixel. And this will learn how to classify the very center pixel using the context together. So once you have this kind of model, then what you should do, you can feed all the pixels and the nearby pixels as a query to this model to classify each of those center pixels, and then they will be classified, right? That should be super slow, as you can imagine. In the last lecture, in the detection, we mentioned that feeding like 2,000 image patches for inference is super slow. So they invented like fast RCNN and even faster RCNN. But here, it's not just 2,000, but it's 300 by 300 is 90,000. So it's not possible. It's very inefficient. And it's not just computationally heavy, but it's also very inefficient because suppose two adjacent image patches and they just move by 1 pixel, then most of those backgrounds will be still the same, and just a new one row or column is added. So overlapped part is very small, and you are actually doing the same operation multiple times there. So this brute force method is not efficient at all. Okay, so what should we do? For training, we may sample a few points instead of the entire pixels, because many of them are overlapped and they are just repeating the same operations. Okay, then we may just selectively choose the sampled pixels and using those sampled patches to classify each of those pixels and then maybe interpolate or do something. I don't know. So they propose that kind of ideas. But then at testing, we still have to choose all, actually infer in all the pixels, and which is still very slow. So this is not a good answer to tackle this challenge. So what should we do? So here we can think of some similar approach to fast RCNN. Should we really infer or train on the patches and we have to repeat all of those patches separately? Maybe not. In the detection, actually, we've done that. We just fed the entire image once and then use the conv representation to do something, right? So encode the entire image instead of the image patch with a convnet, just single convolution networks. And then we can do some classification on each pixels in the later stage. So that's the direction that we are going to try. So here we feed this entire image as input, and we train some convolutional networks. And the output, we set the same size of this image, and each of them are kind of classification scores. So suppose we have 20 classes, then this will be a bitmap of 20 classes, the 20 channels, and each of them has the score for each of those classes corresponding to the pixel. And then we may take the maximum value there. Then we can classify each of these pixels. Sounds reasonable, right? Are we OK now? Not yet. So most convolution networks we've learned were actually shrinking. You may remember that AlexNet, the output size was just 6 by 6, remember? And VGG, it was also small, like the output was 7 by 7 or something. And after that, the GoogleNet or ResNet, still the size of those feature map shrinks. We have more channels usually, but the feature map size actually shrinks. So in this case, we need the feature map or the score map, which is the same size as the input, because we have to pixel-wise classify. So we do require the output size to be the same as the input size for this problem. So we cannot directly use the AlexNet or the VGG or the previous models. So maybe we can do that. Do this then. Design a network with only conv layers without downsampling or stride larger than 1. And we always use the same conv. Recall that we have this same padding options in the TensorFlow conv filters. So we can just keep this input and output size always the same. Then eventually we can pixel-wise classify them to the classes. So given the input size is image size times 3, and then in the conv layers, we still keep the image sizes same, and we may just adjust the number of filters or the depths, which is D and C here. D is the depths, and then in the later, we map it to C classes, so C channels, and then we take the maximum to have this final prediction. So are we okay now? It looks reasonable, right? People tried, but it's not enough yet. So because we do not reduce the size, backprops to the earlier stages are very, very expensive. So in the AlexNet, for example, we had only the 6x6 in the very last layer, right? But you may remember that if we stack the conv layers, the receptive field grows if we go to the lower layers. Remember, 3x3 in the very first layer, and then it becomes 5x5 in the next layer, 7x7 in the next layer, again and again, right? So if we stack multiple layers like this, from 1 pixel here, that becomes 3x3 here, and 5x5 here, 7x7 here. If we use only 3x3 conv. If we use larger filters, then it grows even larger. But it was okay before because we had only 6x6 or 7x7 in the very last layer. So it was small. It was okay. But now we have, in the very last layer, we have the number of pixels, which is like 90,000. And we have to backprop all of those gradients through these networks for all the pixels, which is huge amount of computation. So it's prohibitively expensive. So what should we do? And this is kind of final answer. So okay, it's too expensive to not to shrink the representation. So we can try this, downsampling and upsampling. So when we learn about the context and the shape of the objects and everything here, the semantic stuff in the input images, we shrink as we already done with the convolution networks. So we shrink the map size to half again until very small numbers like this, and then we upsample them again back to the target size, which is the same as the input size. So in the first part, we downsample from the image size h by w. We make it half, make it another half, and another half. So we have smaller representation size here. And then we do the upsampling. But still, we have a problem. For downsampling, we learned that using some average pooling or max pooling or some stride size larger than 1, then we can achieve downsampling, right? How can you implement upsampling? Using the regular convolutional operations, this is not possible, right? So how should we do this other than the fully connected networks? So here are some basic ideas of the upsampling. So one is spreading the values in a deterministic way. So nearest neighbor is, for example, just taking the values to the nearest new dimensions. So here 2 by 2, and we make it 4 by 4. Then only the first and the third rows and columns are existing ones, and we have 12 more new cells here. And just take the nearest values from this original input to just fill them like this. So if we take the max pool from this one back to here, then it will be the same, right? Or we can do the linear interpolation too. In here, we have the average of 5 and 8, something like that. in some deterministic way of filling those empty cells. Or bed of nails is just zero padding. So those new cells are just filled with zero, and we have just the values from the original values to the new target positions. So I think this naming is actually interesting. So they named this a bed of nails like this. We have only values with these nails, and all other places are zeros. And this is in-network upsampling idea. So because we have the conv layers and corresponding upsampling layers like this, they are kind of symmetric. We start from the image size and make it half and make it another half. And then we would like to double it and double it again. So we always have the matching layer within the network. So when you shrink the size, we can remember where we actually take the max value, for example. If we take the max pooling from here to here, then we can remember where actually this 5 came from, like this. And then when we upsample them, we just reuse that information. So this one will be one of these 4 cells, and where it should be. Because 5 came from this part, we put 1 there, instead of just deterministically putting in like this, bed of nails. So yeah, here 2782. So 8 was the max value, and we mapped the 2 to that position among these 4, something like that. So this is also used, but still this is deterministic, just based on the data in the fed to the network. So what we are going to learn today is this one, deconvolution networks, which is the opposite of the convolution networks, where we are going to see that how they are related in the later slides. But basically, you can think that this is the opposite of the convolution operation. So let's review what was the convolution again. So this is just regular convolution. You are given this input image, and if we conv with stride larger than 1, then we usually shrink the image size. So recall that from this 7x7 image, if we perform 3x3 convolution with stride 2, then the output size becomes 3x3. So let's see. We take the 3x3 filter in the very first position here, and then we take these values multiplied with the filter values here, and then we sum all of them to right here. So this is what we've done in convolution, right? And in the second part, the stride size was 2. So we take this part and multiply with the filter values and sum all of them and write the result here. That's what we are doing in the regular convolution, right? Same thing in the last one. So that's how we get score, the size from 7x7 shrink to 3x3. So I would like to summarize this as picking up some things in the corresponding region and summarize and aggregate the values in the output. So I wrote here in Korean, 주워 담기. So this is the picking up in English. So that's what we do in convolution. So let's do the opposite thing to do that. Deconvolution with stride size larger than 1 is an upsampling operator. The regular convolution was downsampling. Here, it's upsampling. How? So take a value. So now we are going to start from 3x3, and we are going to make it to 7x7 using the same stride size and the same filter size. So take a value from the input, multiply with the filter, and spread the scaled filter in the output. So here, from the 3x3 input, we take the very first value, and then we have the filter, some pattern, and we multiply them with this value to right here. Because the stride size is 2, now the output should be located in the next position using the next value, input value here. So multiply with this filter, and then we stamp it here. And again, like this. And if they are overlapped like here, then the values are added, just simply added. So I would say that this deconvolution is kind of stamping. We have the pre-designed, or the based on the filters, we have some pattern, right? Using those patterns and multiplied with the input values and just stamp it in the output. In this way, we are kind of upsampling or expanding our feature maps. So here's another example of deconvolution in the one-dimensional case. So this is the input, just two-dimensional vector. And suppose we have a filter of 3 values here. Then what should we do? In the output, we're just stamping, as I said, taking the one input value here and multiply with XYZ pattern. Then we output here in the same manner, like AX, AY, and AZ. And stride size is 1 here. So we take the next value, B, and multiply it with this stamp, BX, BY, BZ. And they are located in the next position because the stride is 1. What if we have stride size of 2? Similar way. So we take the first value and multiply it with the filter and stamp it here, 1 to 3. And because the stride size is 2 now, we take the next value and write it in the 3 and 4 and 5, like this. And when they overlap, we add those values. Simple, right? In this way, we can implement the learnable upsampling. And these values and filters are determined from the data, so we can always apply to any kind of data sets. But here, I'm going to explain how these are actually related. Very interesting manner. So mathematically, this deconvolution is also called as transpose convolution, which is really interesting. We were thinking like that they are kind of opposite or reverse, but now it's transpose. It's a little bit weird, right? So let's see. So here, suppose we have an input of these 4 values, A, B, C, D, and we would like to do the 1D conv. Corner size is 3, which is XYZ, and stride size is 2, and padding is 1. So because the padding is 1, we apply the padding here. And let's do the one-dimensional convolution. So in the convolution, what we do, we take this filter value, XYZ, and it was the picking up, right? We multiply these values to the corresponding input values and sum all of them. So that was what we were doing with the convolution. So filter value is XYZ. So we multiply them with 0, A, and B because of the padding, and then sum all of them to be the first value in the output. The next, the stride size is 2. So skip the first 2, and then we multiply this XYZ to 3rd, 4th, and 5th values, B, C, D here, and they are multiplied and picked up and just written with just one value here, BX plus CY plus DZ. And this is it. This is the convolution operation. Okay, let's compare this with the deconvolution or the transpose convolution. Now, we have the input of just 2, A, B, and we have the same 3-dimensional filter, which is XYZ. And now, what we would like to do is the stamping. What was the stamping? Take the first value in the input, multiply with all the values in the filter, and then write them as a vector as is. Right? So with stamping, we have these filter values multiplied with A, the first value, and written here. And the next value, because we are doing the stride with 2, the next value will be B times XYZ. So it will be BX, BY, BZ. They are added with stride 2. They are stamped here. And one overlapped value here, so they are just added. So this is what we've done as deconvolution in the previous slides. Now, you can compare these two. The second part, the input part is the same. just the dimensionality difference. But this matrix, with the convolution, it was like row-wise, and now it's like column-wise. So deconvolution is actually the transpose of those convolution. That's what we can observe mathematically. Very interesting, right? It was like a reverse operation, but now it's actually can be proved mathematically that that's a transpose convolution. So in some papers, they call it deconvolution, or someone call it transpose convolution, but basically that's the same thing. Or they sometimes just say it's upsampling, but usually upsampling is using these transpose convolution. So we can use these deconvolution networks to downsample the features from the image like this. From 224, it becomes half again and again until we have some reasonable small size. And then it's upsampled again back to the original size using unpooling here. So this is actually the paper from our university in electrical engineering. The professor Bo-Hyung Han, he published this model in 2015. So yeah, this is straightforward after you just understand how this deconvolution works and how can we actually apply that to this segmentation task. Because we have this labeled map and we have this convolution and deconvolution networks, then it's done like this very simple network. Let's move on to the next model, which is actually very similar. It's called the UNet. So they try to apply this segmentation model to some biomedical domain. So given an image like this, which is some, let's see, some cell, HELA, I don't know what it is, so HeLa cells, they wanted to segment each of these cells and the boundaries. So in the labels, they are, each pixel is labeled like this. This is some particular type of cell. This is some particular type of cell. And in the boundary, they are also annotated as this is the boundary pixels, like this. You see that these are the boundary pixels. So basically, we would like to do the segmentation task on this particular domain, but nothing special, actually, just the same kind of segmentation task, right? Their model is a little bit interesting. So let's see. The encoder part is the regular convolutional part. So nothing special here. Given the input image, which is size 572 times 572, they applied twice of the convolution of 3 by 3. And they used 64 filters here. So the channel size is 64. And interestingly, they didn't use any padding. So the output size is gets shrink, like gets smaller than the input size by 2 always. So because they use 3 by 3 convolution, so in the they applied twice of these convolution operations, then output size becomes 64 times 568 times 568, and then they do the max pooling with 2 by 2. So the image size becomes half, so it's 284 squared. And they just repeat the same operations, twice of the with 3 by 3 filters, and then max pool, again, 2 by 2, and again, until they have this 28 by 28, and the number of channels they use is 1024. So just normal convolution models, very similar to this. They just shrink half always. The only difference is that they don't pad. So within the same group, they still shrink a little bit, like by 2 pixels. Anyway, the embedding becomes 28 by 28 conv features, and the number of channels is 1024. And then they do the decoder, very similar manner. So now instead of the max pooling, they do the up convolution, 2 by 2 here, and then perform another convolution twice. And here again, the size becomes smaller because they don't pad. I don't know why actually, but they don't pad. And then after that, they upconv again in the same manner. So they actually do 1, 2, 3, 4 times of this set of operations and make it back 4 times again. Now, you can observe that I mentioned in the very first part of this lecture that in this segmentation task, the input and output should be in the same shape, right? But now, the input is 572, but now the output is 388, mainly because they didn't pad the image, and every time they apply the convolutions, the image size become actually shrunken. So now the output size is different from the input size. So what should we do? Before we talk about that, actually they applied one more thing here, the skip connections. Skip connection is connecting the input representation to the output representation to the corresponding layer, to the corresponding level of the resolutions. So at the very bottom, the second last bottom here, they applied the, for example, here is 64 times 64 feature map at the output layer of this group. And the corresponding upsample features, they have 56 times 56. So it's slightly smaller. So they take the center 56 times 56 and concatenate them here to make it twice larger. And then they make it back to 512 features using the 1x1 conv. So in this way, they take the input embeddings or the representations from the center to just add them or concatenate them to the deconved or upsampled feature representations. And then they use both of these encodings and the decoded embedding together to represent the segmentation map. So in this way, they can actually take advantage of the multi-resolution encodings at the decoding stage. So it was their main idea. But still, I mentioned that the input and output size are different, but they didn't resolve that issue yet. Let's see. So how what they're doing actually? So we may imagine that if the input size is 572 by 572, then the output should be in the same size, and we have the bitmap of the corresponding classes of those pixels in this input size. But actually, their input and target output size was this. They wanted to segment this size of image, and they expanded this image to this size using some kind of padding, because they know that the output will be shrunken from the input image by this amount. So when they feed this, when they would like to segment this size of image, they actually padded the boundary of those images somehow to make this size. And that's why actually they can freely feed, just throw away these boundary pixels and just use the center. That was okay because they were not interested in there anyway. But instead of filling them as 0 with 0 padding, what they've done is actually reflecting. So here you see that this yellow part is what they are really interested in. The input image is actually this part. You see some line here. So from here to here until the end of this green box, and here until around here. So only this box is what they are interested in, and the original input image. But the rest of them is what they have created by reflecting the input image. So reflecting this image based on this point, they actually increase the input image size like that. This is biologically incorrect, probably, right? It's not reflected like that in reality, but I think they just believe that that's still better than just filling them with zeros, because it still looks a little bit more plausible than just having all the zeros or blacks in the boundaries. So they just reflected that, And these values are kind of temporarily used only when they apply the convolutional operations to learn the representation within this target area only. And then those are just ignored when they actually output. So the output is just based on this center. And because their input is probably too large, they take only some part of that. So in the first batch, they just use this yellow part. And the next batch, they apply this green part. In that way, they can segment each of those images. And then they can just the results can be concatenated to make this entire image back with the the segmented results. But for example, when they feed this yellow part, this extended blue region is used as the input, and the target will be this yellow size. In the next batch, they feed this red here, and then they get the segmentation map for this green part, something like that. Quite smart, right? So to summarize, they extrapolated the missing context here, the boundary of this input image, using the mirroring of the input image instead of the zero padding. And overlap tile strategy is what I just explained. So generating seamless segmentation that only pixels for which the full context is available from the input image. So they are just interested in these yellow, green, and so on, instead of the entire images, including these extrapolated ones. Okay, and here, let's see their loss functions. This is also a little bit interesting thing here. So basically, they are using the pixel-wise softmax. So over the finer feature map, they apply the softmax to the output values on that pixel, and then apply the cross entropy to learn which class they should belong to. So this is the output from the very last layer. Then they take the softmax here, and then that becomes the probability. And then the AK, actually the opposite, sorry. AK is the logit that pixel X belongs to the class K here. And then they take this softmax to make it as a probability. And this is the output of the model. But then they apply the cross entropy, but it's not regular cross entropy. Here it's weighted cross entropy. So if you don't have this Wx, then it will be just regular cross entropy. But they multiply some weights here. So what does this do? So this is our estimated probability of the target pixel. And with using the cross entropy, we would like to maximize the value, the predicted score for that correct class as much as possible. That is the meaning of the cross entropy, as we discussed in lecture 3. Here, they multiply the Wx here, which is defined as this. So what is this? D1x means, given that input pixel, this is the distance to the nearest border of the cell. So the distance to the closest distance to the cell boundary, which is computed by this D1, and D2 is the second thing, is the distance to the second nearest cell. So these two actually gives higher values if the pixel is far from the boundary of the pixel. And this will be very small or close to 0 if they are located in the close to the borders, like these, something like this. Around here, this point is meeting with 3 adjacent cells. And some pixels nearby here are, these distances will be almost 0 because they are very close to the borders. Then what happens with if these D values are small? This value is small, both of D are small, then the value within this parenthesis will be large because it's minus, right? And that means this entire output becomes large, right? So if they are close to the borders, we have larger weights and vice versa. Why should we do that? Border is important. When we segment the cells, inside these cells, it's easy and it's less of interest. but where is the actually end or the boundary of those cells are more important biologically. So they wanted to focus more on those hard and important part of this segmentation task. That's why they kind of invented this weighting scheme. So this is just deterministic function, and they don't learn this from the data, but they somehow designed this to give properly larger weights for those boundary pixels. And in this way, they actually was able to get this good segmentation results on this set data. So that's it. That's their main idea. And the semantic segmentation has a lot of applications. Actually, you can be creative to use this for many of these applications. In self-driving, this is, I know that many of you are from the self-driving lab in mechanical engineering and electrical and computer engineering departments. So you guys are probably familiar with these self-driving data sets and examples with a lot of segmentation stuff. And yeah, many things like virtual try-on is basically mapping the pixels of the body to some other clothing. So suppose this is the input, and then what this lady will look like if she wears this clothes. And then that's basically mapping all the pixels here to some other thing, given that this lady is wearing this clothes. So I'm not going to explain all of these applications, but these are actually semantic segmentation has a lot of interesting applications. And if you're interested in, actually, you can find a lot of interesting papers of doing that. And these are the further readings. So recent progresses in the semantic image segmentation is summarized in this survey paper. So if you're interested in this applications or the task, yeah, this should be a good reading for you. Yeah, we have 12 more minutes, and let's try to finish this instance segmentation before the midterm. So as I introduced at the beginning, instance segmentation is different from semantic segmentation in that we detect all the objects of all the classes and segmentize them pixel-wise instead of the bounding boxes. So these bounding boxes is the detection task that we've done before. But today, we are doing the segmentation instance-wise. So each of these person or the bag or the umbrella, they need to be segmented with these pixel-wise. And each of these different persons or different umbrellas should be individually recognized and segmented. So that's the difference between instance and the semantic segmentation. And here we use the extension of the faster RCNN. So in the last lecture, in lecture 9, we briefly mentioned that this mask RCNN uses the average, weighted average corresponding to the distance between the pixels, the target values, and in the grids, right? You may remember that. We have that in the next slides. Here, they add one more components here. So from the region proposer network, they propose the region proposers here, and then use them to classify them to detect each objects and bounding boxes regress. That was the faster RCNN we've covered. They add one more components here, which is called mask prediction. So yeah, this is what we've seen in the last lecture, that instead of taking the max pooling, they try to interpolate the values in the ROI feature map from its input features using the distance between the pixel and pixel to pixel, or the feature values to feature values, to preserve here's the purpose. Actually, they wanted to smoothly preserve the per pixel spatial correspondence. And that was actually their motivation for doing the segmentation task. Because for a segmentation task, the pixel-wise information is important, different from classification or detection. They just wanted to classify some image small patch. So that much detail wasn't that important for fast RCNN. But here, mask RCNN, the segmentation task, you have to preserve the pixel-wise information as much as possible, smoothly. So instead of taking those max values, they try to use these weighted average scheme for this network. So here, yeah, instead of simply taking the max over the uniformly split ROI, they used linear interpolation, and they named it as ROI align rather than ROI pooling. So for the more details, actually, you can refer to this paper. And here I have the summarization of this method. So given this image, we would like to do both the segmentation and the detection. So this part is same as before for the faster RCNN. They feed this entire image to the some CNN, and they use ResNet. And here, a little bit difference is you may remember that ResNet has up to conv5, but they feed that up to only conv4. The last set is ignored here, not just removed from the network. And they extract the features on conv4. And then they do the same thing here. You may remember from the last lecture. From this map, they apply the region proposer networks and to propose and actually propose the potential anchors for each of those cells. And then here we actually skip the very last set of layers, which is called conv5. And now they apply the conv5 here. That's the slight change from the previous faster RCNN. So they apply the conv5 model here, then the output becomes 7 by 7 from 14 by 14. And then this part is the same. They perform the faster RCNN to classify the objects within this anchor, or regress and adjust the XY coordinates and the width and heights of those bounding boxes. That is just for the fast RCNN part. Now I mentioned that they added one more. It's called for mask RCNN. So here, from this 7 by 7, because this is segmentation, they need to get it back to the larger number of pixels. So they apply the deconvolution and convolution again to have the per class mask predictions like this. So for each of those small image patches, they have the ground truth segmentation mask. And using these deconvolutions, they recover the larger number of pixels, more fine-grained pixels. And then they wanted to map it to those per class mask predictions. So this part keeps the spatial information needs to be intact, because we do this segmentation task, and the pixel-wise information is the crucial here. So we never use the fully connected layers, which mixes all the information from different pixels. So here's the loss function. So the left part is the same as faster RCNN, and only this part is added here. So MI is the ground truth pixel level masks of size M by M, which is 14 by 14 or 28 by 28, depending on what specific model they have used. And these are marked as 0 and 1. If that pixel belongs to that target class, then that's 1. Otherwise, that's 0. And this is our prediction, which is some real number of the same size. Here, the K means the number of classes. So for each class, we learn the mask separately, and we choose the correct feature, the segmentation map using this YI. So yeah, the cross entropy, they use the cross entropy loss here because this is binary classification, pixel-wise. And this YI is multiplied here because this loss is meaningful only for the correct target class. So the object should be there, and those pixel-wise masking becomes meaningful only when they apply the correct class. So this YI, if this YI is 0, then this entire term is ignored, and only for the target correct class, they compute this loss and backpropagate it. And this is another hyperparameter to control the relative importance of these different terms. So here's the examples. So for example, for this object, chair, they also detect these bounding box, but also this segmentation map like this. And this is for this bed, and this is for the chair with a little bit misaligned bounding box. And this is for this baby, something like this. So here's some useful API functions for detection and the segmentation task. So if you are working on this topic for your research or some applications of this, maybe using exploring some of these models would be great. So this is the end of today's lecture. I did that too quickly. So we have 4 more minutes before we finish. So I'm gonna give you the chance for questions.